Hello everyone, my name is Qingfeng Xu. I came from the Anhui University of Technology. Today it's my pleasure to present my work on the Eurosteel. The title of my presentation is A Two-Scale Method to Address Connections in Coupled Fire Structure Simulations. The behavior of structure under fire is very complicated because fire introduces not only strength decreasing, but also the thermal expansion, which causes additional load on the structure. And for building facades, the fire-induced collapse sometimes is not only due to the loss of the insulation resistance, but also due to the failure of other parts like glue layer melting, steel plate detachment, and critical component lost. For a structure system like sandwich panel, it is hard to predict when and where the whole structure may fail because it contains so many different components which may induce the collapse, and these components are in different scales and interacts with each other. For example, the large-scale sandwich panel has thin walled plate and insulation layer which connected by the small-scale screw connections, and the large-scale steel frame is connected by the small-scale bolted connections. So it is hard to simulate such complex sandwich panel system with all the details. It requires huge amount of computational cost. The traditional way to simulate this fire structure coupled behavior is a one-way method. First, we simulated a fire, and we applied the fire curve to the structure to check their thermal and mechanical responses. But for this method, the interaction between the structure and the fire has been lost, as the progressive failure of the structure cannot affect the fire simulation. So we proposed a so-called two-way coupled method. For this two-way coupled method, we divide the whole simulation into several segments. At the end of each segment, we check the failure of structure. If the structure fails, the fire and structure model will be updated in the subsequent segments. For example, in this compartment fire simulation, the whole simulation time is 100 seconds, and the structure failure will be checked every 10 seconds. If the panel failed because of the connection failure, it will be removed in the subsequent simulations, and the fire curve will also be changed accordingly. We compare the traditional one-way method with the proposed two-way method. It shows that the structure may fail much earlier by using the two-way coupled method due to the rapidly changing of the fire. The simulation mentioned here, we use linear spring as a simplification for screw and bolted connections, as suggested in the Eurocodes. But in practical, their behavior can be temperature dependent or even more complex due to contact problem. So we proposed a so-called two-scale method to solve this problem. The idea is we're still using a spring element in a structure system, but the stiffness of the spring element is provided by the small-scale model, which contains every details of screw or bolt connections. In each segment, first, the global scale simulation is carried out, and the translational or rotational boundary condition will be transferred to the small-scale model by a so-called sub-modeling method. Therefore, the instantaneous stiffness of connections in this segment can be predicted, and it will be used to update the stiffness of spring element in the global scale model. In this way, the behavior of the small-scale model is taken into account in the global scale model. But before we implement the two-scale model to a complex sandwich panel system, first we should verify the accuracy of this method. To do this, we create a detailed system model which contains of two plates connected either by a screw or a bolt, and the simulation results are compared with the two-scale screw connection model and the two-scale bolted connection model, respectively. For the bolted connection, all types of failure modes as given by Eurocode are carried out by the detailed system model and the two-scale model. The reaction forces of bolted connections are shown here. The two-scale model and the detailed system model show corresponding behavior for all failure modes, which are tension, shearing, bearing, and punching failure. Similarly, all possible failure modes of screw connections are given by Eurocode has been studied by the two-scale model as well, and the simulation results are compared with the detailed system model. So as the Eurocode, we can find the displacement versus force curves are very similar for these two models, and also no problem for combined shear and tension failure and different temperature cases. So, as described above, the two-scale model can be used to predict failure of both screw and bolted connections. We may need some codes to make this procedure mentioned above automatically coupled. The simulation flow of the two-scale model coupled with fire structure simulation is shown here. The existing FDS to Abacus is able to couple models in CFD and finite element domain, which are fire analysis and thermomechanical analysis. And the proposed two-scale model can be used to connect the small-scale connections with a global-scale structure system. In this way, the failure prediction of structure under fire can be more accurate because both the fire model and the mechanical models in different scales are taken into account. Here I show a compartment fire simulation by using the two-scale model. In this compartment, the facade is using a sandwich panel which is connected with two steel columns and four screw connections, and the failure of components will be checked every 5 seconds. The coupled simulation is shown as here. We can find the fire is successfully applied to the global scale sandwich panel model, and the boundary condition has been transferred to the small scale screw connection model. The reaction forces changing in the small scale model due to the stiffness changing in the global scale model. In this case, all screw connections failed due to the plate bearing. The figure on the left side shows the reaction forces versus time of screw connections with different load step size. In other words, the spring stiffness in the global scale model updated every 2 or 5 seconds, respectively. The results are comparable along the simulation path. However, screw failure times are determined more precisely for a smaller load step. As soon as all screw connections failed, the sandwich panel will be removed in the subsequent fire simulation. So, the fire scenario is changed from a ventilation control to a field control, and the heat release rate increases dramatically. Therefore, the local failure of connection affects the stability of the whole structure, and in turn, the structure failure affects the fire scenario as well. Models in different domains and scales are coupled together. We may reach the following conclusions. All possible failure modes are given by design codes has been studied by the two-scale model. The proposed two-scale model is verified with a detailed system model, and they show corresponding behavior for all failure modes. When a structure with connections are subject to fire, connection failure may be a critical factor of the fire resistance. The two-scale model is able to transfer boundary conditions from the global scale model to the small scale model. Then the mechanical response of the small-scale model can be used to update the global scale model. For a compartment fire, the loss of a sandwich panel may change the fire scenario from ventilation control to field control, which shows the importance of using the two-way coupled method for the fire structure simulation. In the future, structure systems with more components will be investigated. For example, we will use more sandwich panel to check a complex and progressive failing system. In addition, a number of fire experiments will be simulated to verify the simulation results. Basically, that's all my research. Thanks for listening, and I would like to hear your comments or suggestions to my project. Thank you.